Hi everyone, I'm Jin Cao, a PhD student in Carnegie Mellon University. I'm here today to present an instance-aware predictive navigation in multi-agent environments. This is a joint work with collaborators from UC Berkeley and ETH Zurich. To make autonomous driving vehicles run safely in complex multi-agent environments is still desirable but challenging today. Nowadays, a typical autonomous system often involves different modules: perception, planning, and control. Motivated by the recent success in visual perception, we seek the visual signals to guide the driving policy learning and improve planning and control in autonomous vehicles. Let's first describe multi-agent environment setup here. We assume there are n agents in the environment. Each of them has one policy, which is unknown to others. We only control the ego vehicle to react in the environment, while the state of transition depends on the combination of all agents' actions. The major challenge here is that the combination of agents' action is uncertain, leading to different possible future states, and predicting the future status of other vehicles is challenging. In this work, our goal is to enable the ego vehicle drive as fast and safely as possible under such a multi-hypothesis transition in the multi-agent environment. Here, we see an example to explain multiple future hypotheses. We could see the black car or the ego vehicle. They are approaching the crossing. At the crossing, the black car must choose to turn left or turn right, and the action leads to different future status. When the ego vehicle makes such action decision, it should take all possibility into consideration to avoid possible accidents. Now, we introduce the key idea of our work to drive in such a multi-agent environment. In such an environment, to drive safely on the different hypotheses, first, we need to have perception of agent instances and the surrounding environment. Therefore, we perform object detection for instance location and semantic segmentation for surroundings to gain knowledge of surroundings of other agents. Then, the second part of a multi-hypothesis forecasting we use it to forecast the future agent location and the surrounding visual structure at the same time. They are dependent on different possible action combinations. Finally, the forecasted results provide cues to make decisions related to underlying multiple hypotheses. After introducing the high-level key ideas, now we dive into the method design. The proposed instance-aware predictive control has two stages: forecasting and planning. In forecasting, the model forecasts future status based on sampled ego vehicle action and witnessed action patterns of other agents. Have witnessed the two hypotheses of the next step. The model could have sense of multiple future hypotheses. Then, the model forecasts multiple future agent possible location in a single route, together with the likelihoods of agent-relevant events, such as the collision chance between ego vehicle and that agent on the corresponding predicted position. Okay, now we show the overview of the dynamics model used for forecasting. We input a sequence of historical observations starting from the current step back to delta t frames ago. A deep feature extractor gets multi-scale features from them. Then, a multi-instance event prediction module does detection and instance-level event prediction on this frame. Next, by combining with a sampled action sequence of the ego vehicle. The features are used in a convolutional STM module to generate the features for next step. Following that, they share the multi-instance event prediction module, does position estimation and systematic structure prediction on the predictive features for the next step. Also, on each forecasted position, we predict the likelihoods of instance-level events. Besides, the predicted features are forwarded into a fully connected layer to predict the scene-level event probability. Then, by sampling action on step t+1, we could forecast the features on step t+2 in a recursive manner. After that, we have all event and visual structure prediction on the step t+2. In such a way, we could predict the consequences of the full sampled action sequence within horizon of the future. Now, we come to the second stage for planning. With the obtained probability of safety-related events on future steps, we use predefined cost functions to calculate the candidate's cost, and we choose action sequence with the lowest cost to execute. Here, some events are irrelevant with other vehicle agents, while some other events are correlated to other agents' action. We call them scene-level events and instance-level events respectively. In planning stage, we put them into two stages of cost estimation for more robust action selection in the multi-agent environment under multiple hypotheses. In the first cost function, we take scene-level events, such as driving outside drivable area or getting off lane, because with this kind of events having nothing to do with other agents that have very low uncertainty, the forecasting noise is expected to be very low. Here, alpha is a weighting factor to put different weights to different future steps. Then, for the remaining action candidates, we take instance-level events likelihoods of them into the consideration, namely the second cost calculation. It is the key to have a reliable driving policy in the multi-agent environments. The cost function is the sum of event likelihoods of all forecast possible locations of surrounding vehicles. The insight here is to select action sequence leading to low chance of accidents between the ego vehicle and other vehicle agents. This is a figure explaining the introduced planning strategy. The basic idea is to use the low-noisy scene-level event to filter some obviously bad action candidates. Then we use the key instance-level events to calculate the second cost function to determine the final action sequence to execute. Now, we come into the experiment stage. In practice, we work on realistic driving simulator Kala and a video game environment GTA 5. Considering usability of two environments, we mainly conduct experiments on Kala. To quantitatively evaluate the model performance, we follow the evaluation metrics from previous related paper SPC as a reward. We compare rewards from multiple model-based and model-free algorithms. We could see, with only molecular RGB input, our proposed method IPC could beat all other methods on different environment configurations in color. We have more ablation studies and experimental results on GTA-5 environment. Please check the original paper for more details. Now, we show the demo video produced by our method on color simulator. We could see the eagle vehicle learns to avoid the coming vehicle and overtake the car in front of it. Moreover, it could turn at turning smoothly and slow down to avoid collision in many scenarios. We'd like to note here again that the policy is learned without any demonstration. Thanks for coming and listening today. Now we have a QA session. Please let me know if you have any question.